Alrighty, welcome back. After yesterday's just throw a solver on it, we are back in for day 11. So day 11 is reactor. Here's some loud beeping, server rack. Here's our puzzle input. Oh, I've seen this puzzle input in previous years. So here's the names of all the devices, and here's the devices they output to, or rather their outputs. Data only ever flows from a device through its outputs. Find a path from U to out, it looks like. Find every path from U to out. In this example, these are all the paths from U to out. There is no U. Oh, there's a U. Okay. I guess out is just a hard-coded value. So we have to count the number of paths from U to out. So we're going to put 5 in here. There are, I'm going to say 3 ways for us to do this. Obviously, there are going to be more than that, but basically, we can either do, because this is pathfinding, these algorithms are really well established. So we can either use petgraph to build an actual graph and then run an algorithm from petgraph's algorithm module, which would probably work for us. For example, here's an algorithm that just gives us all the paths back. The other option for crates is usually pathfinding, which is basically a similar kind of crate, but it's not really for graphs. Like petgraph is a graph data structure crate. Pathfinding focuses significantly more on the pathfinding. And the way pathfinding works is basically like it lets you set up whatever kind of data you want and then call one of the functions, put in a starting place, figure out how to get to the next place, and eventually get to the goal. So here's a function that is count paths. It gives you a starting location. You can give it the successors and you can get a success condition, and it will count the number of paths for you from one to another. And all you really have to do is give it the way to actually get the next position, which is actually significantly better in our case. So it is really cool to like put this into petgraph because you get .viz out of petgraph. So we could actually just dump like a graph of visualization, which is very fun. But especially for part 1 here, it's just kind of like we have a bunch of labels and we need to get all the paths from one label to another. So it's not really that intense. We could probably do this. All right, I mentioned like there were 3 options. Basically, it's like petgraph, pathfinding, or doing our own breadth first search, which would basically just be re-implementing one of these other algorithms. So I think today for me, I'm feeling a bit burned after yesterday. So I'm going to take the pathfinding route to start with. And then depending on what part 2 is, we can come back. So we can write our parser again as usual. I am still using nom because I like it. If I wasn't using nom, it would probably be a dot lines, be a dot split twice, one dot split for like semicolon and one dot split on spaces. I think we might change it up a little bit today and use a B-tree map instead of a hash map, just to show that it exists really. So separated list 1, line ending, separated pair, alpha 1, tag, semicolon, space, separated list 1, alpha 1, space 1, alpha 1. And I'll just parse the input on the end here and then hit save. My cargo format seems to have broken, which is really unfortunate. Oh, I have a to-do with a semicolon up here. Okay, there we go. There we go. I actually had a syntax error. So doing this, we end up with a vec of string, slice, and string. I'm going to rewrite this parser just a little bit, do something a little bit fancier today, and rewrite the parser to account for the fanciness. So I'm using iterator here, which takes the input, or takes the data, and a parser. And it will keep applying that parser and keep producing values through this iterator in such a way that we can just collect it into a B-tree map. And we can basically, for this iterator, take it by reference, collect it into the B-tree map all at once, or rather, use the collect implementation, the from iterator implementation. We can say that we're done with it, which gives us back the rest of the input that wasn't parsed, map over that iResult with our parsed out value that we've collected, as well as the input. What are we calling these? We're calling these devices. So we end up with this parsed in a B-tree map with the keys AAAUHHH, which I think is right. And then U should be somewhere at the bottom because B-tree maps are sorted. That's the big difference between a hash map and a B-tree map. Hash map uses hashing, B-tree map uses sorting. And then we have to find all the paths from, what is it, U to out. So the way I've set this up is kind of, a little bit awkward, I guess. I've kind of left these in the B-tree map. We have keys that are the device names and values that are the next devices, which means that when we're iterating here, what we have is just the list of next devices. So we end up here with count paths, our original node, which is U, a closure that takes that vec out of the devices. So devices in whatever device is coming in, we get those outputs. We happen to iterate over it to remove a shared reference here, because here we're passing in a string slice. So if we wanted to, we could make this a little bit more clear by maybe not using string slices, because fundamentally we always have to have that string slice, but then we have a reference to that string slice coming in. So if you start writing this like I did here, you might run into some type errors that you're not expecting. But we have a string slice here. We have what is coming in as a reference to that string slice here. Then we're mapping over this with iter, because I'm choosing to not clone the vec, which means that we end up having a double reference in this closure here, when we need a single one to validate this starting condition. So that's why I'm doing this here, just to make it explicit. And when everything is done and ready, our tests are passing. So we'll run this on day 11. We will get a number, which is hopefully the right number. Always nice for it to be a gold star. And then we're into part 2. So part 1, not terribly complicated. I did choose to use pathfinding, which made this like significantly easier for me. But if you look at the implementation, it's really not that surprising, I guess is the way that I would frame it. I think the most surprising part is this successors call. And it's not that the successors call is surprising, because that's basically the function that we gave to this particular algorithm. But there's some caching built in here for us, which is nice. We have our success condition being tested. We are getting the next successors and doing an into iter on them. And then that is being inserted into the cache, which is cool. I think there are some interesting functions that people usually miss in Rust. One of them is actually called successors. So if we wanted to, we could rewrite this to use just successors from standard iter. That's where this documentation is coming from. And successors basically does the same thing that we just did. It just doesn't have that like test condition. So successors with some starting value and some function to produce the next elements will then give you an iterator that you could then repeatedly check to see. There's a couple other functions in the Rust standard iter module that are also interesting. I think successors is probably one of the ones that people are less familiar with, so that's why I mentioned it. There's also repeats and once. And the other one is from function, which allows you to create an iterator from an arbitrary function. So you could mimic something like successors, but with some additional state using from function if you wanted to. Okay, part 2. They know about problematic data patch passes through DAC and FFT. They're still not sure which path is the problem, so they now need you to find every path from server rack to out. However, the paths you find must also all visit both DAC and FFT in any order. This new list of devices contains many paths from server to out. However, only 2 paths from server to out visit both DAC and FFT. Find all the paths that lead from server to out. How many of those paths visit both DAC and FFT? And my question is, how big is the input? So in true advent of code fashion, I think that this isn't a full description of the problem. If we were even going to model it the way that we're currently doing it, I think we would have to use a different method, because basically we're using a simple, like very simple count paths, and there are conditions around that, like there can't be any loops because this doesn't track things like that. This is new input, right? Yeah, okay. So it's new input. So the code we wrote for part 1 is by far not guaranteed to work for part 2 at all. I think that if we just yoink it and try it just to be clear, what we'll end up with is very likely cycles, which means that this will just overflow the stack. The answer for this is supposed to be 2. And if we run this test, we have to modify it to go from server to out, right? SVR. Okay, cool. It looks like there's actually no cycles, which is really good to know because that could have made things hard. Really? No cycles? Interesting. If we just run this on part 2, does it... So it finds everything. And I think that we are basically saved here by having that cache, right? The count paths that we are using has that caching implementation inside of it. And this is an exceedingly big number to have actually computed. I am very happy we don't have cycles though. So just trying to think through formulations of the problem. If we have all of the paths to FFT and all of the paths to DAC minus all of the paths from FFT to DAC, I'm trying to think if we can do some fancy, or not fancy math, but right, if we have 4 paths to FFT from server, do we have to hit FFT first? I guess that isn't defined. It just happens to be second in this graph. I guess it always has to be second. It always has to be second, but it doesn't necessarily have to go through it. Unless there's a bidirectional connection directly between them. Right, FFT and DAC do not have a direct connection. Because otherwise we would have a loop, is what I'm thinking. If FFT and DAC could change order, right, that would necessitate a loop. So if we find all paths to FFT, I guess we could try to figure out which one comes first. That would just be doing the same thing though. Because we have to basically have all the paths to FFT. Of those, all the paths to DAC, and then all the paths to out. And then our answer is what? Nothing we can figure out from that data. We would have to have all paths to FFT and all paths to out, and then all paths from FFT to DAC. We just can't do them independently, I don't think. I was hoping we could do some like tricky math here and be like, oh, if we have the counts for all paths, we have the counts for all paths to FFT, all paths from FFT to DAC. We could like do some math on those to figure out what the count would be. But if we do things like go from FFT to out, we don't know which of those has DAC in it. If we go from DAC to out, if we know the ordering, there would only be 2 then from DAC to out, right? And there's 1 from FFT to DAC. So 2 and 1 and 4 is the answer here. Those are unfortunate numbers because I can't learn anything from the math of 2, 2, and 4. But if we have the original paths and we have the number of paths out, I don't think that math works. And for me, one of the things I want to figure out is there a graph or pathfinding algorithm that I don't currently know about or am not thinking about the applications of correctly? So a bunch of the pathfinding algorithms have weights for different nodes and weights for a bunch of different things. So is there a possibility that we can use another and kind of like weight things correctly to make it work? The number of paths is too big to actually fully calculate it, right? So we do have to do something like we did a couple days ago, where we kept track of how many we had at specific points. There is some potential to collapse the graph, and maybe we get smaller. If we collapse, then we have to keep track of what we collapsed. If we use some kind of pathfinding algorithm with weighting, I don't see how the weighting would work. We don't want shortest paths. We want all paths. So maybe we look at doing something like implementing something similar to count paths, but treat every location as if has it hit each position yet? And if it gets to the goal and it hasn't reached that position or both positions, then we cull it. We do have to do all of the calculations, but we get to drop when we run success, I think, if we do it that way. So we end up with not just like string slices that we're seeing here, but string slices with basically a tuple of whether they hit each node already. So their count paths are just kind of pulled in. We don't need it to be this generic, right? I think that because we're kind of modifying this function, we do end up getting to be, right, successors map sum. And realistically, I feel like we need the cache at the end of the day. Like we need to return this cache because the number that we'll be looking for then is, I guess, the number in the cache that is at quote unquote node like N11, right? If we get to out and it's out 11, then we have succeeded. In this case, what they are doing is the cache is an FX hash map from node type to usize. So if we do the calculations here and we pass it in like that, then I think that works. And actually, I don't even know that we need to modify anything. Now that I think about it, if we set up the problem like this, I think, let me comment out the rest of this. I think actually if we set up the problem like this should end up with what, 2? Yeah, 2. And this is going from server to out, right? And successors then, let's say this is actually 0, 0, right? So we've got our positions here. Maybe this is a struct. Maybe that makes more sense, right? Struct node is label, string slice. What were the two? FXR, FFT, and DAC, right? And we're looking for, we've got our label, we've got FFT, which is false to start off with because we're starting at server. And we've got DAC, which is false to start off with because we're starting at server. And these devices then coming in are just supposed to be nodes, but we have to create those nodes. So when we're mapping here, we basically end up with our next label, right? And node is going to be label next label, FFT DAC device.dac. So this is our next node, FFT or next label equals FFT or next label equals DAC, right? So these are either going to be true because they were true, or we're going to test to see if they are FFT or DAC. And if they are FFT or DAC, then we have hit FFT or DAC. And I think we just return that. And then our test is going to be on node. So our test is going to be label out FFT true, DAC true, right? And I am going to have a bunch of type errors because I messed up my partial eq needs to be derived on node for it to work like this, which is fine. This is all very straightforward. We're using lifetimes in our struct, which is cool. Our input is where these labels come from, which means that this devices is going to live basically as long as we need it to. Let's see, devices, device.label is what we need here. And this is supposed to be a reference to it. No implementation for string slice equals stir? Okay, that's fine. Oh no, you know what the issue is here? These come in as like double references. That's why. And I guess we need to derive hash on this as well for it to work as a node. What else do we have here? EQ. So partial equality is where the equality trait actually like lives. That's where the implementation lives. EQ is a marker trait, which means that it doesn't actually have any functionality, right? If we go look at EQ, it has a bound for trait or for partial eq. And partial eq is actually where these functions live, like EQ and not equal. So the implementation of equality lives on partial equality. And this is a marker trait. As mentioned in the docs, it can't be checked by the compiler. EQ is a trait without methods. And basically you're saying everybody has agreed that you are going to treat EQ as a total equality. If you do not implement it, if you do not implement partial equality in a way that is totally equal, and then you implement EQ or derive EQ, then you've violated the contract of this trait effectively. And there are some notes here around like, hey, this is like upheld. If you're writing unsafe code, you can't rely on this, right? This is basically saying if you write unsafe code, then you are responsible for validating that the result you get out of using partial equality, even if it's labeled EQ, is valid for your use case. So we end up with stuff and things and some lifetime issues. We basically have a closure. And I guess because we were dereferencing it down here, that's really funny. So before we were using things that could be copied. So pulling references off of things ends up copying small strings. We could implement copy for node because node is actually just like the string slice we were using, which implements copy, and bools, which also implement copy. So maybe we actually do that because this is actually just the same as the thing we were using basically. And then when we put move on this closure, we're returning a value that requires that 1 outlives 2. Let's open this up a little bit and take a look. Device has a lifetime of 1, and lifetime of 2 is the closure. So on any given iteration, this is not actually going to produce that many items. So it really doesn't actually matter for us, and we could actually just copy this. Now, one thing that I did overlook is that if the devices that we're working with aren't found, then this will panic. And that it'll panic because of the way we wrote it, right? We panic because we didn't use like .get, which returns an option here, and so on and so forth, right? Because this is line 29, column 20, so that's right here. So in the devices B-tree map, we are looking for this key. We are indexing into it using the square brackets. We could have written .get, which would have returned us an option. I think that it's interesting that that key doesn't exist, because I feel like it should. Let's run cargo test for part 2, and no entry for key. Which key is really my question. And I'm going to log out devices here too, I think. And I didn't implement debug, which is yet another trait we can derive here. So this is claiming that label out doesn't exist. Is that true? No entry found for key. Do we not have out? We don't have out. Out doesn't exist, actually. Out actually does not exist. So, interesting note, how do we cull those then? So basically we just need to not return out as a successor if the next node, so let's do filter map, and we will do if next node dot label is out and next node dot fft and next node dot dac. So if the label is out and we don't have fft or we don't have dac, then this is none. Otherwise, this is some. So if the label for the next node is out and either of the fields that we need to be true are false, then we filter it out. And that's passing our tests. And if we run this for part 2, it runs and gives us a number, as well as a ton of logs. So let's try this number and see if it works. That is the right answer. Sweet. Okay. So we were able to get away basically with redefining what a node is. And by redefining what a node is, we've basically included the additional metadata in the graph, which makes the graph much larger, right? Because then we have, where's our test input? Then we have basically like SVR, right? And SVR really only has SVR 0, 0, right? But we then have this situation going on, right? Where SVR actually doesn't just go to A anymore. It goes to one of 4 different kinds of A. And this is true for every node. So we've greatly increased the size of the graph, but because of our caching and whatnot, because we're keeping track of the counts like we did in previous days, that actually doesn't turn out to be a problem. But it's worth noting that this is happening effectively for all nodes. So we have 4 times the nodes in the graph, or approximately 4 times. We actually don't have server 0, 1, or 1, 0 because that will never happen. And then that means that our goal is only out 1, 1. If we have either of these two that we reach, then we have kind of like ad hoc made it so that the nodes that are trying to go there can't make it. And really the only reason we did this, so we're kind of like expanding the graph in the algorithm, right? Because we only have this list of devices and we are ad hoc like adding this additional metadata in our processing. So the only reason that this if is necessary is because when we go to look for in the next loop, if we go to look for out, which wouldn't have anything, right? It would be an empty vec. This wouldn't exist. So we have actually options here, right? We could, if we wanted to, do devices dot push out, or I guess insert, right? This is a B-tree map, insert out with an empty vec, right? So this should technically, if I'm thinking about this correctly, also work. Expected option found unit, because this is filter map. If I remove that, then it needs to be not filter map, and this needs to be the actual value. So we get rid of a little bit of logic here. We get the same answer. So you can see that that's all this logic is doing. All this logic is doing is making it so that we don't need to insert this outline. And actually, I think I like this better. I think I like setting up the data better, because then we get to remove some of this. The code is a little bit smaller. Out just becomes a node that has no sort of child nodes. So the actual like new data generation that we're doing here is not all that much, especially for producing such a big number. So count paths, basically we have a cache, we keep the counts like we did in previous days. We set up our data in a way that we can use. We use a new node definition. We have a definition of what successors is, where we insert this extra data for FFT and DAC, whether we hit those nodes in this path or not. And then we have our win condition or our goal condition, which checks to see if this C is the out label with both of those nodes having been touched. And this expands the size of the graph, but it doesn't really matter. And we run our whole solution in 268 microseconds. So I don't actually think that we can cull this sooner. I think we have to do the full counts. There might be a way to do the calculation differently, but I can't think of it off the top of my head right now. So I'm going to drop in these benchmarks here. We're looking at, I guess, 100 milliseconds, or milliseconds, 100 microseconds for part 1 and almost 300, so 277, we'll call it, for part 2. And I'm reasonably happy with that. I think we've already done the work of like building the caching that we otherwise would have needed to in previous days. So I'm comfortable using this because it just adds that cache for us. And by cache, we mean, which day was it? Yeah, it was day 7. On day 7, we actually wrote the code to keep track of these values as we were iterating. And that was for the splitters day. So since we've basically already written this code, and this is basically what that function is doing for us, I was comfortable using pathfinding today. But that's it for today. Tomorrow is the last day. It is day 12. Day 11? Wait, today's day 11. Sorry. I live in the past. I'm doing this at 9 p.m. at night. So tomorrow's day 12. We'll see what they give us for day 12. And I hope you've had some fun so far. I'll see you in the next one.